it's about time. So I'm going to go ahead and start with the video here. One thing, not everybody's back, that's okay. One thing I want to mention before we kind of hop into everything is there's kind of been a trend I've been noticing on a lot of the homework success as I've been trying to grade it. I've already made a point to point this out. But oftentimes, my goal of homework is to make sure that you're understanding how to see how you're working on the current material, how you're understanding it, to make sure you're guided on the right direction there, and I try to give pointers. But oftentimes the pointers that I have to give aren't even about the new material. It's a lot about like mistakes like these, or like Calc 1 mistakes that take place, which is kind of an issue because I mean we're wanting to continue to move forward, but there's a lot of these things that are happening that are like should mostly have been addressed or not be worth dealing with anymore, and so it just makes it hard to continue to move forward when there's so many of these things that we can't even really get to the heart of the problem at hand. So I guess maybe one way to solve this is just please be sure to not do everything last minute and just make sure you're taking your time on things to make sure you think clearly. Like really just think about the problems, right? Because again, if we were to take this, for example, and just really sit and think about it for a while, this should not make sense for us. Just take any example that you can think of and put it in there. I've done like 9 and 16, this failed, okay? To be true, right? But I've seen this several times. And yeah, it's just a problem. So don't just keep like, you know, kind of climbing your way to the next thing while just like forgetting all the stuff as you move along. Like really try to build on it, because that building is what's ultimately going to let you excel. Just a note on that. Really just be careful. I try to set up the homework so you can do them like, you know, you can go home and just do the one page, go home, do the other page each day. So that might be helpful, instead of waiting until the last day. I'm not sure who will decide if anybody does do that, but just so like just to help you, if you weren't sure. Okay, cool. So with that being said, here's the averages again. If you want those, I've had those up for a bit, just so you can answer for them. So I wrote 72.36 is the average from test 1 before any homework, and then this is after, and the average before any sort of adjustment of test 2, 64.44. With the 2 problems taken out, it went up to 75, and then average after homework is like 78.7. So you can kind of compare your score to that, see how you did. Overall, these numbers are too bad. I don't really like that one much, but I think my test was just a bit hard for that. So yes.
Is the homework like the one that's on Fridays? Or is it
No, that's the extra homework. The mandatory homework doesn't count for any sort of extra credit. That's just the mandatory homework is for grade. That is purely for the book problem. If you do book problems and you show your work that you did them, and then just like write down the answers, then I want to give some points. And you can see it makes quite a bit of difference. It's like a 4% difference in grades. So cool. Okay, I'll leave that up for now. We're going to continue on to fun section today, which is going to be 9.3. Okay, which is about separable differential equations. Okay, so separable differential equations. So up to this point, we haven't been able to solve any differential equation. We've just, I've checked to see if the solution might work. I found a way to approximate solutions or kind of see what they look like, but we do actually have methods to solve these problems. And one of the methods we have is specifically in the case where the equation is separable. Let's say a separable differential equation. Okay, so whenever we're dealing with separable differential equations, I have a differential equation that's of the form dy over dx equals f of x times g of y. Okay, now this form is going to be very helpful to us. So if you have a differential equation that's in this form, this is very good. And the reason why this is very good is because I can take, right, so I have a function of x and I have a function of y. They don't intermix. There's no x's in this one. There's no y's in this one, right? They can just be completely separated from each other. What this means is that I can take, so this is dy over dx. Remember when we talked about differentials, I can always multiply each of those parts, right? So I can kind of separate the dx from the dy. So that's what I'm going to do here first. I'm going to take both sides of this equation and I'm going to multiply this by dx. When I multiply this by dx, what's going to happen is I'm going to get dy equals f of x g of y dx. Okay, good. Now, when I'm at this point, right, still doesn't seem like we've gotten anywhere, but we will get somewhere because I have f of x dx, which if I just had that, I could do the integral of that. I could take the integral because it's just a function of x with dx, I can integrate it. So I'm going to take both sides of this equation and divide it by g of y, where I'm going to get d of y over g of y equals f of x dx. Okay, so let's recap what's happened here, right? So I multiplied the dx both sides and I divided a g of y for both sides. And now I have everything with a y on one side of the equation, and I have everything with an x on the other side of the equation. So I have dy over g of y, just a function of y here, and then I have f of x times dx. They're both separate from each other, separated, right? That's why it's separable, right? To x on this side, y on this side. This is perfect because now I can take both sides and integrate them, right? Because if this is just a function of x dx, I should be able to integrate that. And if this is a function of y, which is 1 over g of y, but obviously depending on what g of y is, I should still be able to integrate this. So I get dy over g of y, right? Then I should be able to integrate this, right? And what that's going to result is that both of the dy and dx, these on, those are going to go away. And so we're just left with some function of y and some function of x, which in some cases I may not be able to solve that, but in others I might be able to solve that directly for y and get an answer, right? So, of course, just kind of talking about this as it is, it's we can't tell exactly for sure what's going on, so we're going to do some examples here. So, any questions on this concept at the moment? Anything? Okay, you kind of see what's happening there. We're going to take some examples. Okay, cool. So let's start out with, and I'll just do some of the problems here. So we're going to solve some differential equations. Okay, so this is number 2. We're going to get this. So we have the equation dy over dx equals, and we're going to have x times the square root of y. Okay, so this is the equation I'm given, right? And it asks us to solve it. It doesn't just say approximate the solution. It doesn't say test the solution. We have to find what actually is the function that solves this thing, right? So what we're going to need to do first is, right, ask the question: is this a separable differential equation? Right? Can I separate on this right side? I have a function of x and I have a function of y, which are completely separate from each other. There's no x with the y. It's not adding. There's nothing weird going on. I can separate. Okay. So, just like with what's here, and maybe I'll do kind of I multiply the dx first here, but maybe I'll divide this y part first. So I'll do the square root of y on both sides. And that's going to give me, or maybe we can just do both at once. So I'm going to divide that square root of y for both sides, and I'm going to multiply dx on both sides. So I'm going to be left with dy over the square root of y equals x dx. And maybe an even better way to write this is I'm going to have y to the, if I have the square root of y on the denominator, how can I rewrite that? To the negative 1/2. Okay, great. Can I integrate this now? Right, they're both separated, right? So now we should be able to just integrate it. Right? Because I have one integral problem over here and one integral problem over here. So let's do it. Okay. On the left side, how am I going to integrate this thing? What's it going to turn into? Good. Because we get y to the 1/2 over 1/2, but then the 1/2 on the bottom is 2. So we get 2y to the 1/2, right? And technically we're going to have a plus c. So maybe I'll write that for the moment. Technically it should be like a plus c1, right? And this is going to be equal to, what's the integral of x dx? And then plus another constant, c2. Okay? Both sides, they're indefinite integrals, so I should have a constant on both sides there. However, let's think about this real fast, right? If I take just, so I have the c1, I have the c2. If I subtract c1 from both sides, right? What is c2 minus c1 going to be? It's another constant, right? It's just another number, and it doesn't matter, right? I mean, you could have your two different constants and combine them in some way, but it may just be easier when you do these sorts of problems to just consider 1 plus c on one side of your equation, right? So I'll just say the c2 minus c1 I'll just call it plus c, right? Again, you could skip this step if you want. So, you know, if you just wanted to skip this part, just go straight here, that's fine. But I wanted us to understand that technically there should be a plus c on both sides, but since I can just move it over, I can just write it as 1 plus c. Okay, now, can I solve this equation for y? I would hope so. Or we don't have to, but it looks like we can, right? If I wanted to solve y in this equation, what would I do? Good. I'll divide by 2. Okay. So when I divide by 2, I'm going to get, so what am I going to get when I divide by 2 on this side? Good. So we get plus c over 2. Now maybe just for the sake of trying to, I'm going to put this as C3, right? Because if I take C3 divided by 2, again, that 2 can just kind of be absorbed into the constant, right? It's just a number, right? So it doesn't matter if it's divided by 2, it's still just some constant. So I get 1/4 x squared, you can do c over 2, you can just, again, just put a plus c here. Okay, I put C3 just to make sure they're distinguished technically, but you can really just carry that plus c later. Okay, and if I want to solve for y, what's my last step? So this side, we're just going to leave it with y equals this left side squared. Okay, which is going to be, what's 1/4 x squared squared? Okay, and then we're going to have plus this, which I guess you could leave it in this form if you want to. I'm going to expand it out more, but so 2 times this, so 1/2 c x squared, and then we're going to have plus c squared. Okay, now if you're wondering why don't I change c in this case, well, it's because I have c squared and I have c, right? So in order for this differential equation to be true, I definitely need this number in here to be the square of whatever this guy. Okay, I can't just put one random constant here and another random constant. So those, they need to be related, so I can't just change it. If I'm just multiplying or dividing a number, that's fine, but if I square or do anything else crazy, I might need to be careful. Okay, so again, this is the solution to that differential equation, right? And if you're not convinced, I'll show you. We'll check to make sure, right? So let's see. Okay, so right, our solution we got was y equals this 1/16 x squared minus plus 1/2. Plus squared. Okay, so I want to make sure this works with that. So what is the derivative of my function going to be? Plus cx. So 1/4 x cubed plus cx, and then that plus c squared. Okay, good. So that is the derivative. And my claim is that this should be equal to x times the square root of y, which is the square root of, now I wrote it in this form. Be reminded that this is the same thing as 1/4 x squared plus c squared, right? Now what's going to happen between the square root and the squared? They're going to cancel. So you get 1/4 x squared plus c outside of that square root. Is this a true statement? Absolutely. Good. So we just verified the answer that we found, this y does indeed satisfy this equation, right? Now, it doesn't matter what c is, you can put any c you want to in there, it's always going to work. Okay? Any questions on this? Good? How's that? Not too bad, hopefully. We'll do another example, of course. Make some room here. Okay, good. So let's see. Okay. Let's see. Do we want to do another one like that, or let's make it a little more. We'll make it a little more interesting. Let's do number 6. So number 6 in the book, we have du over dt equals, now we're going to have 1 plus t to the 4th power over u t squared plus u to the 4th. Wait. Ut squared plus u to the 4th. Okay, so this is our problem. Okay. So this is the same, it's the same question, right? We're going to solve this, right? So the question is, can I separate this? Yes. Okay. How do you say that? How do you know? We can factor the t squared out of the denominator. So I'm going to rewrite this as 1 plus t to the 4th power over u plus u to the 4th squared, which then of course I can rewrite this as 1, let me do 1 over u plus u to the 4th power times 1 plus t to the 4th over t squared. Just like that. Okay. Now now, it's separated, right? So we could actually solve this, right? So remember, this is equal to du over dt. So I'm going to, right, so like in the last one, we want to like move this over here, and we're going to move this dt up, right? So what should I do with this 1 over u plus u to the 4th power? What should I do with both sides to move it? Good. So we'll just multiply both sides by u plus u to the 4th, and then I'll multiply by dt as well. Just go ahead and cancel that dt, move it over. So we're going to get u plus u to the 4th power du equals, and then we're going to have, can we simplify this expression here a little bit? How? Okay, fantastic. So at this point, we are going to want to integrate this. Maybe. Okay, so let's integrate the left side, integrate the right side. What is the integral of u plus u to the 4th? Du. Anybody? Okay. So that's completely fine. I'm gonna write it as 1/2 and 1/5, but it doesn't matter either way. Okay, and then I'm gonna leave the plus c for a sec. What is the integral of 1 over t squared dt? And what's the integral of t squared dt? Okay, now this is not going to be easy to solve for you, right? And that is completely fine. You can try if you want to, but since we have a u to the 5th power, this is not going to be very simple at all. So we can just stop. Okay, if you can solve for y easily, go ahead. If you can't, I will leave it, right? Just like here, I can't really do this. This, and this maybe is what we'll call a, call a implicit, equation, which we've experienced before. This implicit equation gives us that derivative. Okay. Does that make sense so far? Okay, fantastic. So if you want to check it, you could. It takes a little bit more time to check, but it does indeed work. So just like using our implicit differentiation rules. Okay. Now, let's take an example that we learned before and truly prove it to ourselves that it worked, right? Who remembers? Who remembers this equation? Right? This is our population equation, right? Our ideal one, at least. I can't remember if this one has, maybe they wouldn't do that in the next section. The more complicated population ones like we did in 9.1. But let's take our basic one and try to solve this, okay? Is this separable? Yeah, there's not even a t, right? I mean, there's dt, but there's no t, there's just k, but k is a constant. So this is absolutely separable, okay? So if I want to solve this, right, what should I do to, what should I do? Okay, so I'll do dt over y on both sides, same sort of motion. So the dt will cancel out on this side, so we're going to get dy over y, and we're going to get, this is equal to k dt. Okay, good. Now what do? Integrate it. Good. So maybe I'll. Okay. So what is the integral of dy over y going to be? So close, guys. Is the natural of the absolute value of y. Gotta be careful. Okay. And this is equal to plus the integral of k dt. Let's see. Right? Okay. Can I solve for y here? Absolutely. So we're going to take e, raise it both sides. We're going to be left with y. That's just going to give us y flat out. And we're going to get e kt plus c is our solution. Okay. Now, e to the kt plus c. This doesn't quite look like what we're used to. It looks, I mean, it has e to the kt with this plus c up here. Do we? What is it? Yeah, there's no y0 term, but there will be, right? What we're gonna do at this point, can I take? Is there something I can do since these are adding together? Yeah. What is that? This is the same thing as e to the kt times e to the c. Okay? This is the same thing. But this is a constant, and in this case, we can make this our y0. That e to the c term. Because that's our constant that goes up front. So we get y equals y0 e to the kt. Okay, again, just renaming constants, but if you wanted to just like rewrite it as c instead and have c to the kt, that's fine. I just named it like that so we can see the connection. Okay, but using these methods, we can solve those equations that were a bit harder for us earlier on, or we didn't really know how to work with it. Okay, where we get that. Okay, this was a whole almost is that 3 seconds at this point? I don't know. Doesn't seem like it should be that long. Okay. Good. Any questions on that? Okay. I wanted to at least do one example where we had the have a natural log in there. Figured why not the best one? Okay. Good. Now this is all fun to do, but obviously our examples aren't just going to stop at, you know, like you have some random constant, right? We're going to want to have a specific solution in some problems, and so we're going to want to solve for that particular solution, whatever it is. Okay, so remember we also have to deal with some initial value problems. Maybe I'll pull up the whole thing here. And this is just going to slightly extend the work we've already done in this section of problems. Okay, so we'll just do one example now, so you can get the idea. We're going to do number 12. Okay, so number 12, it says find the solution of the differential equation that satisfies the given initial condition. So number 12, we are given dy over dx equals x times sine of x over y, where y of 0 okay. Is this separable? Yes, it is. So if it is separable, we want to separate it. So I'm going to take both sides. What should I do to both sides? If I want to separate it. We're going to multiply by y to move it over, and we're going to multiply by dx to move it over. So we're going to get dy, y dy equals x sine x dx. Okay, next step. Integrate it. Thank you. Okay, so we're going to integrate this. What's the integral of y dy? Good. We get 1/2 y squared, or y squared over 2. And this is going to be equal to, okay, now this one, right? We're going to remember our integration by parts a little bit to do this, right? What do I need u to be? What do I need to, yeah, so we're going to let u be x, and we're going to let d be the rest. So what is du? Du is going to be dx. We're going to let b be. Good. Okay, maybe a good time to mention, there's also a thing where a lot of you are very loose with where your dx is at. If it's inside the integral, there has to be a dx there. And if you have du or dv, whatever it is, there should be a dx term on it. Okay? And if it's not those situations, then there should not be a dx there. Okay? Again, another one of those things where you just need to really think more and be careful, but might be a really no. The dx's go here with the du dv, not here. Okay, so that's going to leave us with u times b negative x cosine x minus the integral of v, which those are that's equal to plus, and then times du. Okay, and then what is this? What is the integral of cosine x dx? Sin x, and we get a plus dx on the end of it. Okay, so we get this. Can I solve for y? Yeah, might be nice. So I multiply 2 on both sides, and maybe I'll call this c1, just distinguishable. We'll get y squared equals negative 2x cosine x plus 2 sine x plus c. 2 times c1 is going to be our new c. And then to solve for y, what do? Take square root. So we're going to get y is square root of negative 2x cosine x plus 2 sine x plus c. Okay, so that's our y. Are we done? No. We wanted the specific solution that passes through y of 0 equals negative 1. So I'm going to get a particular c for this problem. Okay? So this is our y, right? And we have x's in here, right? And we know that y of 0 needs to give us negative 1. Let me think about this one real fast. Well, it does. May not exist here necessarily. I think it just depends on, because obviously the square root would be plus or minus, right? Because either way, if it's plus or minus, that should still give you the correct answer. So in this case, where y of 0 is going to be negative 1, right? So we're one to look for the negative square root in this case. So I want negative 1 to be equal to negative square root of, and then we're going to have, okay, now what is x again? 0. So we get negative 2 times 0 times the cosine of 0 plus 2 times the sine of 0 plus c. Okay. Right. So this just becomes 0, right? Because negative 2 times 0 from cosine of 0 is 0. So we get negative square root of, and then sine of 0 is 0, so we just get negative square root of c. So essentially, I have negative 1 is negative square root of c, which is the same thing as saying 1 equals the square root of c. So what is c? Well, not plus or minus 1 in this case, right? If you're squaring both sides, it just has to be 1. If I put negative 1 in there, it wouldn't work. So we just get c. So c is 1. Great. So, and of course, again, we want to kind of keep track. It shouldn't be a big deal in most problems, but in this case, since there's that negative there, we'll want to attach that since we want a negative 1. So our final answer, maybe I'll put some orange here. We're going to get y equals negative square root of negative 2x cosine x plus 2 sine x, and then not just plus c, but plus 1. I'm fine with this. Questions, comments, concerns? What is it?
Yeah,
That was our condition. Y0 is -1.
okay, and why put the negative instead of this
Here?
Yeah.
Well, because, so whenever I'm taking a square, right, technically it could be plus or minus at any time, so I have to write the plus or minus. In this case, I want a -1, so I would use the -1, right? Because if I use the plus sign, it wouldn't give me the minus. I can't take the square root of something normally and just get a negative number out, right? Unless it's in like this particular sort of scenario where I have like my square root or something. Okay. So. Good. Again, other ones we may not have to worry about that sign thing, but hopefully when you're in there, you can kind of feel it out and adapt to it. Cool. That's the basic gist there. Again, if I was on like this problem, for example, right? If you're like, oh, these problems might be pretty hard, right? We did this one was pretty easy, right? And you might just be given an initial condition of like y of 0 equals 3, right? Well, in that case, I just need 3 to be equal to y0 e to the k times 0. Well, what's k times 0? 0, and what's e to the 0? 1. So I just get y of equals 3, right? So then in this case, it would be 3. Okay, which we've kind of seen before, but again, they should be pretty straightforward, but it's all the same idea. Just plug in the numbers and see what that constant's supposed to be. Okay, good. Makes sense there. I have some good problems on that homework for you to do in this section. So great. One last thing is there's going to be some some word problems that are emphasized here, which aren't going to be too bad. But they all focus on this idea of mixing, where I have some sort of space, so I'll write it down there. Some problem here. Okay, where I have some sort of space where it could be a tank or it could be just some sort of bubble, whatever it is, and inside this, coming into this area, I have some sort of something coming in, right? So there's something coming in, and then there's also something that might be coming out. Okay, now this whatever's bringing in and whatever's coming out is going to be bringing, like, for example, there's I think the one homework I have is like where you have a tank of water, and I have there's going to be some water that's going to be coming into it that's bringing some sort of salt content into the water. Okay, and it might contain this amount of salt per liter, right? That's coming into the tank, right? But the tank itself is also emptying water at a specific rate, right? So let's say it's I'll kind of take their problem just to get some numbers here that makes sense. So they're given that in their problem they have like 5,000 liters of water in the tank, and coming in to the tank, there's going to be so it's dripping out at, what's the rate, 25 liters per minute, and it contains a salt content of 0.03 kilograms per liter. Okay, so there's 25 liters per minute of water coming out of that faucet, and there's 0.3 kilograms per liter of salt within that water. Okay, and if I multiply these together, I can understand how much salt's coming in per minute. And then what happens is there's also an amount leaving that's at the same rate. So it's also leaving at 25 liters per minute, right? And so the question becomes, how do I figure out what, how much salt, like what kind of the flow of salt is through it, right? There might be some initial amount that's in it, and there's some that's coming in, there's some that's coming out. How do I calculate for all this? How do I factor it all in. And the way that we do that is we use differential equations, of course. Why would I be talking about it here otherwise? Like these situations, right? You're going to be given some numbers, right? dy over dt, you're going to have a rate of salt, water, whatever it is that's coming in, and you need to subtract the rate of whatever's going out, right? So you might have some consistent amount of thing coming into the tank, which will give you kind of the positive part of the rate, but then we're also going to have something that's coming out, and so I need that to be the negative. Okay, so I'm going to use this general framework to be able to calculate how the salt changes over time, or how much and the problem we'll do here real fast, the carbon dioxide changes over time in a room. Okay, so let's do this last example. So we're going to do, this is number 46. Okay, if you want to read that one in the book, feel free. It's a good example to understand what's happening. I'm going to do this one in the book. So we have a room. So maybe I'll just do a little block here. So this is my room, and the room, there's air in this room that has a volume of 180 meters cubed. And it contains 0.15% carbon dioxide, which I'll write as CO2. It's kind of like the abbreviation there. And this is initially. So if we start the system off at 0, there's 0.15% of carbon dioxide in the room. That's the starting point. Okay. Now there's fresher air that's coming into the room, right? So I'll kind of draw this little arrow. There's some fresh air that's coming into the room with only, that contains 0.05% of carbon dioxide, and that is flowing in at 2 meters cubed per minute. Okay, and the mixed air, there's going to be air that's also flowing out of the room that's going to flow out at the same rate. Now, obviously, we don't know how much CO2 is going to be flowing out, right? Because it just depends on how much might be in there and you know, what's coming in and what's being forced out. It depends, right? We don't know, but we know that it's coming out at the same rate. This kind of air that's leaving air, whatever you want to call it. Okay, so the question is, we want to find the percentage of CO2 in room as function of of time. Okay, great. So this is going to be a problem, so I need to work it out, right? But to set it up, I'm going to use this differential equation, right? So y is going to be whatever my function is, and that's going to be the percentage of CO2. That's the function we're looking for. Okay. So first, I need to know the rate of CO2 coming in the room. Okay. So if there's 0.5% of CO2 in this 2 meters cubed per minute of the fresh air, how do I figure out the amount of CO2 that's in that air coming in? Multiply it, right? So we're just going to take times. So we're going to take that 0.05%, and we'll leave it in percent. You don't have to change it to the decimal. 0.05 times 2. So we're going to get 0.1 meters cubed per minute. This is CO2 entering here. Okay, but now we need to figure out rate out. Okay, now we don't know how much, we know how much there is initially, but we don't know how much carbon dioxide there is at any given moment. Okay, so to figure out the percentage of CO2, right, we're going to take the the amount of CO2, which we don't know yet, which is going to be our y of t, right? That it's that amount. We're going to divide this by, so we have some meters cubed amount of CO2, right? So we're going to take this and we're going to divide this by 180, right? Because that's how much of the air that it takes up, right? So it takes up, so that's how much of the percentage is compared to the air, right? So I take y of t over 180. And then we're going to multiply this by the rate that it's leaving, which is also 2 meters cubed per minute. Or I can write this as, what's 2 over 180? 2 over 180, anybody? Yeah, so we have this over 90, right? Now, from this point, we have, so this is the amount entering and this is the amount leaving. This is our differential equation. Is this separable? So I have 0.1 minus y, just I write what y of t was just y over 90. Is this separable? Yeah, absolutely. So I can separate it. Maybe to simplify it first, I'm going to get a common denominator here. So we're going to get, let's see, 9. 9 minus y of t over 90. Again, just multiply 90 by that, got the same denominator, and we're going to solve this. Okay, from here, I want to get this part with the y of t over to this side, so I would divide it. And divide over here to give us dy and multiply the dt equals 1 over 90 dt. Okay. Everybody kind of imagine there, I'm just solving the equation at this point. What is it? That's was from earlier. It was, yeah, I was just showing that guy before I got there with the 2. Yep. And then, so now I can integrate both sides, which to save work here, this is going to be negative natural log of 9 minus y of t equals 1 over 90 t plus c. We solve it. I'm going to take e of both sides, or let me put the negative sign over first. E, so we get 9 minus y of t equals c e negative 1 over 90 t. Subtract 9, flip your negative sign, we're going to get y of t. Okay, so the hardest part is just setting this up, and then it just becomes like any other problem we've done before in this section. Okay, so again, make sure you're doing rate in first, which should just be a number, right? You should be able to calculate that easily, and then minus rate out. In this example, your rate out would have been y of t over 5,000, right? Because I want to know how much salt there is per liter in there, and if I know there's y of t amount of salt, I take that and divide it by 5,000. So that would be that. And then I take it and multiply by 25. That would be my rate out. Okay. Yes.
There ever be a problem where there's
Multiple outs? I didn't see one when I was looking through here. There might be a problem where there's multiple ins, but that would just be that's just more numbers. That's not changing the y of t. If there's multiple outs, you wouldn't have that in this case. So again, this is the hardest part, and once you get that